We propose a novel transformer model for the task of unsupervised learning of skeleton motion sequences. To avoid expensive and time-consuming annotation for supervised learning, recent studies have focused on unsupervised learning techniques for pre-training. First, to generate a well-separated representation space according to the characteristics of the motion sequences, pre-training is performed using unlabeled data. The pre-trained model can help tasks using motion sequences achieve good performance with a small number of labeled data or a short training time. We focus on an unsupervised pre-training method suitable for action recognition. Several methods exploit RNN-based encoder-decoder models. Their encoder is designed to extract the information of the input motion sequence to help the decoder reconstruct corrupted sequence or predict the future frames. However, they have difficulties in extracting global contexts because of the long-range dependency problem. Another recent approaches introduce contrastive learning schemes. In these methods, the performance is highly dependent on the selection of the encoder model, because the contrastive loss does not induce detailed learning in the local dynamics of the joints. To tackle these problems, we introduce transformer-based pre-training method. If well designed, we can expect the attention mechanism of the transformer can help learn both local dynamics and global context. The first model which applies transformer architecture to unsupervised action learning is H-transformer. H-transformer learns to predict the instantaneous velocity of joints for masked frames. The model has limitations in learning temporal long-range attention because the instantaneous velocity can be easily obtained from the adjacent frames. And the model architecture has an attention mechanism between internal body parts. Global body movements and person-to-person attentions are not considered in the architecture. Therefore, their performance is not the best among the existing state-of-the-art methods. We design a novel transformer architecture, GL transformer, and a novel pre-training strategy suitable for motion sequences. And we verified the performance on the downstream task, action recognition. For the input motion sequence, we disentangle it into local motions and global translational motion. The center joint contains global coordinates, and all other body joints are represented as relative positions from the center joint. Through the transformer blocks, the temporal attention is applied between the frames. If there are multiple people, motion sequences of others are attached along the spatial attention axis. The spatial attention comprises both global and local attentions. They are attention between joints, attention between body and joint, and attention between people. We first extract features from the motion sequence through embedding layers, the global translation embedding layer and the joint embedding layer. The learnable positional embedding is added to the sequence embedding and fed into the transformer block. Our model comprises n-stacked GL transformer blocks. In the last block, the final motion sequence representation is obtained by passing through two-layer MLP. And our proposed pre-training strategy is implemented through prediction heads. In each GL transformer block, attention mechanism is implemented in both spatial and temporal multi-head attention mechanism. We design a novel pre-training strategy, multi-interval pose displacement prediction. The strategy is to estimate whole body and joint motions at various time intervals. We first select multiple frame intervals, and GL transformer is trained to predict the magnitude and direction of the pose displacement between the current and the selected frames. We visualize the learned attention map to verify our model. The spatial and temporal attention maps are averaged over 300 evaluation sequences. Each head attends a different temporal range. For example, approximately neighboring 10 frames and 5 frames are highlighted in the second and the third attention maps. The right figure illustrates the average attended frame distances of each head. In each block, more heads attend to distant frames when the model is pre-trained with intervals 1, 5, 10, as compared to when the model is pre-trained only with interval 1. For the spatial attention map, the first and 26th indices are utilized for the global translations of each person. Overall, the proposed model learns the global relationships at shallow blocks and learns fine-grained relationships at deeper blocks. In some heads, the 1st and 26th indices appear to be attended differently from other joints. In addition, several components are organically designed to operate main strategy effectively. Most of the existing action recognition methods employ a fixed-length motion sequences by extending or shrinking the sequences. In our method, we utilize an attention mask, so that our model can learn the natural joint dynamics across frames and capture speed characteristics from diverse actions. Joint order information plays a more important role in skeleton motion sequences than in the case of sentences or images. To this end, we propose a tight positional embedding method to use order information explicitly in every GL transformer block. We evaluate our model with linear evaluation protocol with 3 widely used datasets. First, we conduct ablation studies to demonstrate the effectiveness of the main components. Every component in the table has role in increasing the performance, and the final performance of GL transformer substantially exceeds that of the H transformer, exceeding 7.0% for X sub and 11.0% for X view. When we leverage person-to-person attention, it improves the classification accuracy in both one-person action categories and two-people categories, especially the performance increases more in the group of two-people categories. Furthermore, natural speed motion and tight positional embedding also boost the accuracy. Next, we compare our approach with the state-of-the-art methods for unsupervised action recognition in NTU 60, and our method outperforms all previous methods by a notable margin. Our model achieved the highest performance on the other 2 datasets. Note that NTU 120 is composed of more detailed action categories and Northwestern UCLA has a small amount of training data with one-person actions. In addition, we compare the results from the semi-supervised setting. GL transformer exceeds state-of-the-art performance in both evaluations using 5% and 10% of the training data. In conclusion, GL transformer architecture and the proposed pre-training strategy successfully capture the global context and local dynamics of motion sequences and yield state-of-the-art performance. In future studies, our model can be extended to a model for learning various skeleton features together, such as the position and bone, to encode richer representations. Furthermore, our model can be pre-trained with a large number of skeleton sequences extracted from unspecified web videos to be more generalized, and can be applied to various downstream tasks dealing with human actions. For more details, please refer to our project page.